right, Precalc, we're going to use the fundamental theorem of algebra today. You don't have to remember this as this name. We're in lesson 2.5. Fundamental theorem of algebra. Our essential question is, are you able to use the fundamental theorem of algebra to determine the number of zeros of a polynomial function? We've kind of already discussed this. If f of x is a polynomial of degree n, where n is greater than 0, then f has at least one 0 in the complex number system. Linear factorization theorem. If f of x is a polynomial of degree n, where n is greater than 0, f has precisely n linear factors. Let's put this into real words. If I have, this is one I always go back on, x squared plus 7x plus 10, I know this can factor to be x plus 2, x plus 5. Notice this was a 2. There are 2 linear factors. And if I was to solve this, I would make it equivalent to 0. And when I subtract, x would be negative 5 and x would be negative 2. So it has 2 as the exponent. It has 2 linear factors and it has 2 zeros. Now, sometimes these zeros are not real numbers. They are imaginary numbers, and we'll have to watch for that. So the first question is asking us to do just that. Okay, counting multiplicity, confirm this that the second degree polynomial function f of x equals x squared minus 6x plus 9 has 2 zeros. X equals 3 and x equals 3. Well, to prove that, all I would do is solve this, x minus 3, x minus 3. And I know that the 0 that's going to come out of the first would be 3, and this one would also be 3. We used to call that a double root. Now we're just going to show it as multiplicity. Multiplicity. So last year in Algebra 2, we had a theorem that told us if we had imaginary numbers, like 3i, that you would also have a negative 3i, the complex conjugate theorem. So this is true. It says confirm that the third degree polynomial function f of x equals x cubed plus 4x squared plus 9x plus 36 has 3 zeros. Well, remember that formula we used to use in Algebra 2, x squared, oops, that's a minus the sum of x plus the product. It's always best to find the imaginary numbers. When I add 3i and negative 3i, I get 0. When I multiply 3i and negative 3i, I get 9i squared. But remember that I squared is equal to negative 1, so I cancel this out and make this sign change. Now to write x minus 4 as a 0, we just have to change that to x plus 4. And I'm going to go ahead and multiply by what we just found, x squared plus 9. And we have to FOIL here. X times x squared is x cubed. I'm going to keep it in line in descending order. 4 times x squared is 4x squared. 9 and x is 9x. And my last terms are 36. So I took all of the zeros and I plugged them back in using that fun little formula from Algebra 2 and putting it back into here. So kind of tying in from what we did in 2.3, example 3 is getting a little tougher. They're telling us to find all the linear factors and list all the zeros. So we can take our p's over our q's to find out. So these are all the factors, my possible zeros are all the factors of 54 over 1. So remember that's p over q. This is just a 1. So I can list all the factors of 54. 1, 2, 3, 6, 9. Yes, there's a lot of them. It looks like we have 18. 3 goes into 54 18 times. We have 27. 2 goes into 54 27 times, and 54. Now, we can take all of these numbers and use synthetic division to see what works. And remember, I also told you sometimes you will have your TI, and you could put this in your Texas Instrument 84 plus calculator and see where it passes. So I'm going to do that very quickly and see what my guess would be out of all of these numbers provided right here. When I put mine in, it looks like it's going through -3 and +3. So I'm going to try those using synthetic division. If I try -3, I have the numbers across 1, -3, -7, 21, -18, and 54. I know that it's a factor if its remainder is 0. Multiply up, add down, multiply up, add down, multiply up, add down, multiply up, add down, multiply up. Yes, this works. Now, something cool that you can do is see all these numbers that we have left over. We could usually, you could rewrite those as x to the 4th. But you can take those, and I know that in my calculator it showed that 3 and -3 worked. I already used -3. So I know that x plus 3 is a factor. So I'm going to start writing my factors here. Okay, but now I'm going to go ahead and use this and try that 3. So I'm going to put 3 here. I know that if it works, it's going to have a remainder of 0. Drop it, 1, multiply up, add down, multiply up, add down, multiply up, add down, multiply up. So I also know that 3 works. So if a +3 works, we're going to show that as x minus 3. But we're still not done. We only have 2 out of the 5. So how do I find the rest of them? So what I'm going to do is I'm going to take these numbers right here. Remember, this was the x to the 5th. So this would have been the x to the 4th. So now I can start this as x to the 3rd and rewrite it as a function of x over here. Are you able to factor that? Let's see what happens. When I cut it in half, I can take out an x squared, and we get x minus 3. Ooh, look at here. I can take out a 2, and we get x minus 3. So when I write this together, I have x squared plus 2 and x minus 3. So here I can write one more x minus 3, so it looks like we had a little multiplicity or a double root there, and x squared plus 2. Now, I know all the zeros here, but for this 0, x squared plus 2, because we did write it as a product of linear factors, so now we have to list all the zeros. I actually have to solve x squared plus 2 for x in order to get an answer here. X squared equals -2. When I take the square root of each side, x equals plus or minus I root 2. So I can write all my factors. I know that this is a -3. I know that this is a +3, and we have double root or multiplicity. And it looks like I have a positive and a negative imaginary root 2. So my zeros are in green. My linear factors are in blue.